Okay, so I just taught you that with a conservative force, that the path didn't matter. It was path independent. Alright, well, all that mattered for the work was the work only depended on the initial and final coordinates. And for such a system, we can define what's called a potential energy function. I'll show you how to do that. And it ends up being a way that we can see if a force is conservative or not. So let's take a look at that. So imagine we have a mass or a system of particles, and we have a force acting on it. So maybe a force acting on a mass, something like that. And it is moving in what we'll call along the x-axis. We showed that we could find the work done as the integral from the initial position to the final position of that force F of x dx. And what we have shown is that that is also equal to the negative of the change in potential energy. So go back and check out the videos, or maybe do some reading if that isn't quite clear yet. I explained it in the previous video. Let's make another definition out of this delta U, or change in potential energy. A delta just means final minus initial, so U final minus U initial. And so we can set that equal to this right here. We need to keep the minus sign, so let's throw a minus sign over here. It's equal to the integral of f of x dx. Okay, what we get from that is that the work done by a conservative force acting between members of a system equals the negative of the change in potential energy associated with that force. Basically, the change in potential energy is negative when the force and the displacement are in the same direction. And an example of this would be an object being lowered in a gravitational field. Or maybe a spring pushes an object toward equilibrium. Think about that one. A spring pushes object toward equilibrium. It had a bunch of potential energy, right? It was compressed, we're saying. And then later at some other state, it's not compressed. We had a negative change in potential. We lost some of our potential energy and it turned into something else. So what we can do is say that we can define a potential energy function as, we'll just look at one direction, x, as minus the integral from the initial position to the final position of f of x dx. And we're going to add this constant u in here. We called the value of u initial is typically taken for 0 for what they call a reference configuration. It doesn't matter what we assign to it, because all that is a shift, right? If we look at a mathematical function or something, this is just a shift up or down. This is our constant that we get from integrating something. And all we're looking at is the change in u. Therefore, that's going to involve our initial and final positions. It's not going to involve this. So let's take this down to the infinitesimal level. We can say du is equal to minus f of x dx. Do a little rearranging, and we get f of x is equal to minus du dx. Alright, this says if we have a potential function that we can take the partial derivative. This doesn't say partial, but it ends up being the derivative in the direction of the potential we're concerned with, is going to give us our force, and it should. So we can check this. We know what the force of a spring is, right? Let's see if it comes out right. If I take the derivative of the spring potential with respect to its displacement, what do I get? That'll be d dx, and then what's the spring potential? It is 1/2 kx squared. Now integrating drops this down to a 1 after we multiply this by a 2, so those cancel. What do you know? We get minus kx. So we just verified that if we take the derivative of a potential function and it is conservative, then we get back the force. So you can do that with the force of gravity, right? So we know what this looks like. It looks like mg. If I took minus derivative of the potential due to gravity with respect to, we'll do y in this case. That's going to give me d dy of, we've learned that this is mg delta y. That's the potential energy of some object in space with some mass at some distance delta y above what we're calling y is equal to 0. Taking this derivative with respect to y just makes this vanish and go to 1, and we get the force of gravity is equal to mg. We just showed that yes, f of g is conservative because the derivative of its potential function gives us back the force.